Hey y'all, welcome to lesson number 2 of Mr. Smith Physics Online. Little bit of refresher review from what we covered last time. So number 1, visible light is just one part of this electromagnetic spectrum, which is a whole range. This spectrum, all these different wavelengths are on the spectrum. They have different frequencies, different wavelengths, but they all travel at the same speed. They're created, these electromagnetic waves are created when we have a charged particle that is accelerating, right? Usually oscillating or vibrating back and forth. So if I have like my little charged particle, right, and it oscillates or vibrates back and forth, goes like up and down or back and forth, right, then I create an electromagnetic wave, which is this wave in what's called the electromagnetic field. Now, I wanted to add in a note here to make sure that you guys understood this. The frequency of the wave that we get, the frequency of the electromagnetic wave that we get, depends on the frequency of oscillations of the charged particle that's creating it. So if I have a charged particle, right, that's oscillating or accelerating, right, then it'll create an electromagnetic wave, and the frequency of that wave depends on the frequency with which this goes back and forth or up and down. Depends on the frequency of its oscillation, right? So this has a certain frequency by which it's going up and down, a certain number of times it goes up and down in a second, and that is what would determine, right, the frequency of the electromagnetic wave that we'd get. Now, if you remember, right, frequency times wavelength gives us the speed, and all these waves move at the same speed. So that means that if I have, the speed is always going to be the same, and the frequency is determined by this, and that means that by that same nature, the wavelength is actually also determined by the frequency that you're given. Right, and we can actually calculate that, and we'll be doing that later on, is kind of using that equation we went over last time to calculate 4 light waves. Given a certain frequency, can we calculate the wavelength of it? Okay. And then the last piece is that we kind of talked about how these waves can carry energy, right? And the greater the frequency, the more energy that wave carries. That's kind of what we talked about at the end. Now, what's really weird about this, and what I want to start today talking about, is that these waves are pure energy. They have no mass. No mass, right? So how does that work? So how can something without mass, right? And these waves can also travel through massless vacuums, right? So they don't even need to like travel through air or something with mass. But how can something without mass carry energy? How can it be just energy? Right? If we remember what energy is, it's a measure of change or the potential for change. And previously, when we've talked about energy, like kinetic energy or gravitational potential energy, right? We've had mass as like a key component of that, right? We have some mass that's moving or has the potential to move. So how can it be that something without mass at all can exert a force over distance, can do work, can transfer energy, right? How can that happen? How can something without mass transfer energy, right? Well, electromagnetic waves can. So, and to get into what that actually looks like, we have to understand the motion of a wave, right? The motion of a wave is something like this, and I've got a little kind of demonstration. I'll show you this, but we have a wave. Right? The wave itself is moving this way, but any individual particle, right, of that wave, any bit of that wave, is only moving up and down. It's only oscillating up and down in the same position, right? So if it starts here, after one cycle, it'll have returned here, right? Now, I added a link to this on Classroom. This is like a little bit of a wave. It's called a wave on a string simulator from PhET. Right, and it's kind of cool, very satisfying. And here I have a wave that's being created. It has a certain speed, right, which is traveling along. It has a certain wavelength and a certain frequency, right? Now, if I slow this down to slow motion, boom, right? Then we can see that we can follow along with any one of these points, and it just goes up and down, up and down. So it oscillates up and forth, right? So the physical medium, or the medium that the wave is traveling in this case, it's a string, right? In the case of an electromagnetic wave, it's this thing called the electromagnetic field, right? So any piece of that field, when a wave is passing by, it just goes up and down, up and down, up and down, right? So the medium itself is just going up and down, but the wave, this wave actually travels, right? And this wave travels at a set speed that's determined by the medium. The speed of light is 300 million meters per second approximately, right, through a vacuum. And if I increase the frequency, right, they increase the number of wave pulses per second, right, but the speed at which they're traveling still stays the same, right? So here I have more wave pulses traveling by a certain spot per second, but the actual speed stays the same. And the same deal, right? Each point is still just going up and down, but this wave is traveling. Okay, so That's how a wave moves. And the key thing is that there's no net motion of the medium. Every piece of that medium that's traveling through starts one point and it just goes up and then comes back down, right? It starts and finishes at the same point, so there's no net motion, right? But the wave itself, right, moves forward. So no wave, no any type of wave, sound wave, you name it, water wave, has mass. A light wave, no mass, right? Waves don't have mass. They are just a transmission of energy, right? They can radiate or pass energy. That's what waves do, right? They're this movement or this potential to move, right? That is kind of traveling through a medium. Okay, that's what a wave is. So to kind of visualize how this can work to actually exert a force on something, exert a force over distance, and therefore do work and transfer energy. I want you guys to picture this. Is probably my favorite analogy that I like to think of when I think of waves. So here I have a wave and it's moving this direction, right? Moving to our right. Okay, we've got this little tuber dude. We'll pretend it's like a water wave, almost like a big water wave. We've got this little tuber dude in here. Okay, now this guy here he is just sitting here, and any one of these particles that make up this wave, right, they're just going up and down, up and down, up and down, up and down. But this tuber, right, if he can sit in this little nested piece of this wave, if he can sit in there, then even as these are going up and down, well, as this starts to go up, right, and these guys over here go down, what's going to happen to this tuber, right? Well, he's going to start to move in this direction, right? So all of a sudden, this wave, even though each particle is only moving up and down, it's all of a sudden caused this person, because he can sit in this little, or they can sit in this little spot here, it has caused them to feel a force over distance. It's caused them to move. It's transferred energy to them, right? So this wave is able to transfer energy. It's able to exert a force to a particle. Now let's say that this tuber can't actually move here, right? Let's say that he's somehow tied down to like a rock here, right? So he can bob up and down, but he can't actually move forward. Well, what would happen in this case is as this wave goes, right, as this part goes down and this part starts to go up, he's going to rise, right, until he's at a trough. So in this case, he would move up and down, right? So if he's kind of locked in his position there, right, then he won't necessarily travel forward, but he will travel up and down and up and down. And this, the motion of the tuber that we end up getting has to do with a few things. It has to do with, is he free to actually move, right? Is he free from other forces, and is he free to move? Or is he kind of constrained? And it also has to do with how he kind of sits in this wave here, right? So with that in mind, and so just considering here, so just like massless electric fields can exert forces on charges and massless magnetic fields can exert forces, electromagnetic waves, these oscillating electric and magnetic fields, can also exert forces, right? So even though the field itself doesn't have any mass, it can still exert a force, and it can move other things like this tuber that have mass, right? So it can transfer energy, even though it doesn't have mass itself, right? Which is kind of cool. So that's kind of how light waves can move and transfer energy, and how they can be just pure energy and no mass. Now, we mentioned that higher frequency waves carry more energy, right? And this is not because they move these tubers faster, right? Because light has the same kind of speed, but rather because they can move more tubers per second, right? So if we think of a tuber that's free to move, right, then it's going to move more tubers, right, per second. Like the higher the frequency, the more tubers it moves per second. Or if we think of the tuber bobbing up and down, right, then if we just looked at this tuber here, right, there's more crests passing by per second, so he moves up and down more times per second, right? So either way, this tuber is moving more times per second, or there's more tubers moving per second. Either one of these situations means that higher frequency waves, right, can carry more energy. Okay. Now, in a lot of cases, we'll see these tubers kind of bobbing up and down when light waves interact with matter, because a lot of times matter is kind of constrained by other forces, especially in like more solid things. So these tubers will bob up and down. In matter that can kind of move more easily and is free to move, then you'll see something like this. So in like a gas, for example, it'll add to the average kinetic energy of that gas. Okay. So now I do want to kind of point out what gets kind of challenging or tricky with a tuber sitting in this wave, right? So here these tubers are all the same size. Here they kind of sit comfortably in here. They sit really comfortably in this guy. But here all of a sudden, right, they start to get a little cramped in there, right? It's harder for this wave to kind of grab onto them and move them. because of how small that wave is. Okay, so that's an important thing that we need to keep in mind when we think about how these electromagnetic waves interact, right, with matter, right, with things with mass. How do they actually interact with them? And to dive a little deeper into that, we're actually going to start taking a look now at the electromagnetic spectrum. And this is really kind of the big takeaway from today's lesson, is I want you guys to have a good understanding of what this is, the different parts of it, the different kind of sizes and scales that we're working with, and why they're important, right? So once again, kind of tying back, just a general overview, right? We have starting with the longest kind of wavelength and the lowest frequency, we have radio waves. Then getting a little bit shorter wavelength, higher frequency, we have microwaves, then infrared, then visible light, right? Then ultraviolet, then X-rays, then gamma rays. Now these are kind of broad categories with which we break these down into, right? There's not just one type of gamma ray, there's not just one type of microwave, there's not just one type of visible light. It's a continuous spectrum, right, of different frequencies and wavelengths, right? Now all of these, I should mention, I can't stress enough, all of these will travel at the speed of light still, right? So as I increase the wavelength, right, I decrease the frequency, right? As I increase the frequency, I decrease the wavelength, right? They're inversely related. As one goes up, the other goes down. Yeah. So in any case, one thing of note, kind of tying this all together, if we have a charge that's oscillating at this frequency, right? So if I have my charge that's bouncing up and down, right, at this frequency, right, 10 to the fourth, that would be what, 10,000, or would that be one? Yeah, 10,000 hertz, right? So 10,000 cycles, vibrations per second. If the charge is vibrating at that frequency, right, then I get a radio wave, right? Pretty easy. If it's vibrating at this frequency, then I get an X-ray, right? And if it's vibrating within this range of frequencies, then I get visible light, right? So depending on the frequency of the oscillations of that charge, I get a certain frequency of light, which gives me then, because they're all traveling at the same speed, a certain wavelength, right? Some of these wavelengths, just of note, and this is important, you guys will learn a little bit more about this in the reading, but some of them can pass through certain mediums a little bit more easily, can be transmitted through a medium a little bit more easily. So Earth's atmosphere only kind of allows some of these to pass through and reach Earth's surface, right? So radio waves pass through pretty easily. And then around the visible light range, that passes through pretty easily as well, some infrared and some ultraviolet as well. A lot of microwave getting blocked, and all of these higher energy, high frequency waves end up getting blocked, right? Which is very good because these can actually, if you guys know anything about how X-rays can be dangerous, or gamma rays especially can be dangerous, it's a good thing that these get blocked by our atmosphere, okay? So diving a little deeper into these, this is the general scale of things, right? You can see the size of radio waves can be quite large, right? They can have wavelengths that are measured in lots of meters, right? Up to 1,000 meters, right? The size of like mountains. And then getting down to gamma rays, which are incredibly small, right? They're at the scale of atomic nuclei, right? So not even an atom, right? The nucleus of an atom, right? And everywhere kind of in between. So just if you can kind of picture like the size of a needle point, like think of how small that wavelength is. A needle point is so fine, right? And then getting even smaller into the size of a protozoan. Well, what is the relative size of a protozoan or a molecule or an atom? One way to kind of visualize those sizes, and I've kind of put this in here, this is from the University of Utah. I used to use this when I teach biology. It gives you a good scale for kind of atomic things and molecular things. Okay, so a needle point, right? If we think of the size and the scale of a needle point, right, we are looking probably at smaller than a grain of salt. So needle point somewhere like in here, right? If we're getting down to the size of protozoans, right, then we're getting down to like this guy, okay? So needle point is like grain of salt. Then we get a little bit smaller, right? Now see how those compare to like a coffee bean, right, or grain of rice. And then if we want to get a little smaller, right, down to like the size of, for example, let's see, what is our next point? We go to protozoans, to molecules, right? Molecules and then to atoms. So going from there, from like protozoans, right, to, Oh, sorry, protozoan. Yeah, okay. Then we're getting down to the size of like a molecule. Man, that is getting small. Wow, yikes. Okay, so a molecule now into the size of some of the larger molecules, right? Hemoglobin, tRNA, phospholipids, antibodies. Right now, we're getting down to the size of molecules, right? Things that can act on this kind of scale, right? And even smaller, like glucose. And then down to the size of atoms, right? We're getting down to that's the size of an atom. And then if we go back to here, right? Gamma ray is even smaller and smaller than that. So you're zooming in, and we're getting down to this very, very, very small wavelengths. So if we think of how matter is actually made and how things are made up, right? Here we have like this is a very small scale, a little bit larger scale, right? Then we have larger molecules, right? Then we have kind of large single-celled organisms. And then we have like actual physical things, things the size of butterflies, humans, so on and so forth. So thinking about the size of that wavelength, right, relative to what we were talking about with our tuber up here, right? The size of the wavelength kind of determines the size of the tuber that we can fit in here, right? The interaction that it has with that matter. So if we have a gamma ray, for example, that is going to interact with things, right, that are at the atomic level, right, at the level of an atomic nuclei. X-rays, right, are going to interact with things that are at the atomic scale, okay? Ultraviolet is going to interact with things at the molecular level, things like DNA, right? Visible light is going to interact with slightly larger molecules. Infrared is going to interact with even larger, right? And it's still interacting because we're all made up of atoms, right? But it's similar to here. It's like this is a different interaction than this. Okay, this is a little bit more smoother, a little bit more languid, right? Whereas this is a little bit more highly energetic. Okay, so the size and the scale of these depends on how it can interact with the world around it, right? With the matter that wave is interacting with. Okay. So one thing that I want you guys to do is I would like you guys to actually just, after I say this, I want you guys to pause the video and I want you to go to your microwave. And I want you to take a very close look at your microwave. If you guys aren't aware, a microwave uses microwaves to heat food. All right, so go ahead and pause, take a look at your microwave. Just at the very front side, I want you guys to see if you notice anything. Okay, so hopefully you guys saw something that looks like this. Right now, every microwave, either unless it's like a solid, like a metal case in front of it, but they shouldn't have just glass. Right? They shouldn't have just glass. They should have some kind of a little grating in here, either a metal grate or sometimes it's like just a heavily painted like kind of sticker on there. Okay, but it's like these little kind of black pieces, right? So you have glass and then black pieces. Now, the reason for these, right? The reason why we have these is because number one, we want to be able to see what's cooking in the microwave, right? So we need to have some transparency to where we can see. Right? But why have those little black pieces in there at all? Well, what we have, right, is if we have microwaves that are operating at the scale, right, of about a butterfly or so, right, that's the wavelength, okay, of a microwave approximately. And this is used to heat water in your food, right? It gives energy to water molecules, heats them up, right? But we don't want those to, they can pass through glass, right? And we don't want those to pass through. If we're standing by the microwave and those pass through, it's right, they'll start to heat us up. They'll start to cook us, right? Which is bad. But what happens is the spacing, right, of these and how tightly spaced they are makes it that these waves, right, because of the size of them, they can't actually get through those holes. They can't pass through. They get blocked. They get absorbed, right? And so that's why you have that grating on your microwave, is to kind of protect you from the microwaves that are being generated, right? So that's why microwaves are actually incredibly safe, as long as you keep them operating as they're supposed to be operated. Similarly, we can use others of these radio waves. For example, are used for radio. The radio in your car, right, is transmitted. So those sound signals, that digital information is transmitted using radio waves, right? Your cell phones, any calls that you guys make, are transmitted using these. If you have satellite TV, it's the same thing, transmitted using microwaves. Okay. X-rays used if you go to the doctor, right? So we can use these waves to transmit information, right? Same with visible light. We can transmit information to our eyes with visible light, the wavelengths that we can actually see right? And the thing with visible light is those wavelengths, right, that are within that range are the wavelengths that we can actually pick up, right? That our eyes actually have the biological tools to absorb those wavelengths and register that they're what they are, so we can actually see these colors, right? Light itself does not have any color, right? It is rather the picking up by the nerve cells, photoreceptors in our eyes, sending nervous signals to our brain that tell us that we are seeing a color, right? It's actually really cool, and we'll talk a little bit more about color later and how that works. But it's just a certain frequency of this light that we happen to be able to pick up and see as a color. Our brain processes that to see a color, right? This is why if you have a colorblind person, right, for example, they don't see the same colors, right? Their brain, they don't have the physiological tools to pick up those wavelengths, right? So they can't actually see those colors. It's kind of crazy. They can't sense that those colors are there. It's like they can still see those objects, but they can't sense that those colors are there because they can't pick up that. Just like we can't see, right? These are all coming from the sun, all these different wavelengths, especially infrared, ultraviolet. They're passing through still, but we can't see them, right? We don't have the biological hardware to see them. However, there are other animals, notably like insects, can actually see near ultraviolet wavelengths, so just past purple on the spectrum. They can see those ultraviolet wavelengths, so they see a flower in a totally different way that we see a flower, right? It's incredible. In fact, I didn't think of this before, but how bees see flowers. If we look this up, it's actually pretty incredible, right? Something that may look, right, just like a yellow dandelion to us, they actually reflect ultraviolet wavelengths that a bee can pick up, and so it has a totally different coloration to it, right? Has a totally different coloration to it. Now, we make these images by actually using kind of sensors that can record ultraviolet wavelengths, and then we use after imaging to create colors to say, hey, this is like a different actual color. We don't actually know what it really looks like to a bee, right? But it really is incredible. They see things that we can't actually perceive, right? I mean, could you imagine if we could see microwaves, right? Whenever your microwave turned on, it's like it would be like this crazy like flash, and it's even crazier because there's microwaves coming from your phone. There's like, right, it would be a lot of kind of overload, and we'd see fundamentally different things. But like, how can we use, for example, how can we see these? How can we pick these up? And we use these to take all sorts of kind of pictures of the universe and the things that are creating these wavelengths, right? So, for example, one interesting thing about infrared wavelengths is that some infrared wavelengths are actually created and given off by like humans, by anything with heat, anything that has heat kind of within the temperature that you find here on Earth. As it kind of dissipates that heat, it can give off infrared wavelengths, right? So it's actually emitting like, so right now I'm giving off infrared wavelengths, right? And if I had a specialized kind of camera or sensor that could pick up those infrared wavelengths, then I could see, right, which parts of me are hotter, right, that are giving off more of that infrared wavelength, versus which parts are cooler. And so you can use this to actually have like essentially night vision, right, where you can see like here's some elephants, right, and this is just an infrared camera, right? It's picking up these areas on the elephant are warmer than its ears. It's warmer than the ground, right? Mammals are going to be having higher internal temperature than like the surrounding environment typically. Okay, so here we see the ground is cool. The area near the bottom part of the elephant, near its heart, is going to be warmer. Its trunk is pretty warm. Its face is pretty warm. Its body is pretty warm. Its back, right, is less warm. It's giving off less of that infrared radiation, right? And if we look at the ears, this is maybe my favorite part, is you can actually see the veination in the ears, right? Where you can see those blood vessels that are delivering, right, blood to the outer parts of those ears. And the outer part is very cool, right? And part of this is because these ears actually allow elephants to cool themselves, right? Warm blood is pumped out there. It kind of dissipates. There's a large surface area. It interacts and gives off some of that heat to the surrounding environment, right? So it stays cool. Right? And we can actually pick that up using this kind of infrared imaging. It's pretty amazing, right? So, in any case, there's this whole variety of like the spectrum. We can only really see what's invisible, but we actually have sensors that can pick up all these other wavelengths, and we can use these to tell us a lot of stuff about the world that we see around us. And so it's pretty cool. I've attached here kind of a link to this NASA site that talks all about electromagnetic energy and electromagnetic wavelengths. And I definitely recommend watching this introductory video. And as a part of your homework, what I'd like you guys to do is just do a little bit of research on some of these different wavelengths. I'd like you guys to pick one, right? And you're just going to record like a short video, no more than a minute, just talking about what is that kind of general wavelength, why is it important, what's it used for, what's its relative scale, right? Other things like that. There's more information kind of on the classroom link, but I want you guys to pick that, record a short video of yourself just talking about it, and just learn a little bit more, dive a little bit deeper into one of these different kind of forms of electromagnetic waves, right? Electromagnetic radiation, right? So that's that. That's the electromagnetic spectrum. We'll continue to kind of reference this. These are all sorts. They're very important, and it's very important to understand that, you know, even though we have this whole spectrum, right, which are defined by their wavelength and their frequency, and they interact with the environment in a different way because of the size of their wavelength and their frequency, they are all still electromagnetic waves, right? And so they all exhibit the same behavior that all electromagnetic waves have in common, right? Which is that they're created by accelerating charged particles. They have a specific wavelength, specific frequency. They all travel at the same speed, the speed of light, right? But based on their differences, they'll interact with the world around them and with matter differently, okay? So that's why, for example, and we'll keep talking about this later, this is why ultraviolet rays, right, they can cause sunburn or eventually cancer, right? X-rays as well can cause severe cell damage and cancer, right? And that has to do with the scale of these, the wavelength of these, and how they interact with the matter that makes us up, okay? Thank you guys for tuning in. I hope you guys have been enjoying this time so far. Definitely a few kind of like shout outs. Number one, shout out to Sydney and Jalen for my first Cooking with Mr. Smith. They tried to answer my bell pepper question. Haven't quite found a satisfying answer yet. Doesn't have to do with the gender of the fruits. I looked it up. But it does seem to be, based on the scientific research that I did find, it seems to be a little bit random. It seems to be almost entirely random. And also what I'd like you guys to do is if you could send me an email about any suggestions or questions that you guys have, let me know what you guys think, how it's going, things that you would want to see, things that you might want to change, any questions that you guys have. Send me an email and let's do that. I think for the office hours, I'm probably going to move towards doing more just like reach me via email, and we can schedule a Google Chat or a Google Meet if you guys would like. But otherwise, it's a little weird to have like everybody calling in on a Google Meet at once from different classes. I don't think that works quite as well. So in any case, thanks for tuning in. I'll see you guys next time.